Best. Hello, Adam. Nice seeing you connected. Please try to speak something.
Hello, can you hear me?
Barely, but it is problem on our side. Let me try to fix it. You are speaking from a little podium box, not from the powerful.
Oh, okay.
So it was speaker number 1. Speaker number 2, please try to speak. Nothing.
Hello?
Speaker number
Can you hear me?
3. Please try.
Can you hear me?
Nothing. Speaker number 4.
Hello?
Please try.
Hello?
Test. Adam, please
Can you
try
hear me?
to speak.
Can you hear me speaking?
No, hear it. Okay, then I'll return to the number 1. It's not powerful, but at least something. Let's connect that you can speak and you can hear.
Hello?
Okay. Very, very low, but something. Okay. Well, thank you for joining. I hope that others will watch it in the recording because you make foundation for the homework. So there are three subjects for today's meeting. The first one is kind of answer key for the homework. So I will share three codes. First answer key code that will reproduce the expected outcome of your homework. At least one in the class was able to get it in a final format as a function of frequency of set, and others who submitted just did it like a numbers table or several data. And then there will be 2 other codes, which is our original code that we described a week ago that we used for the homework, and it's minor modification with use of so-called rotation frame. So the plan is I see. So the plan is that I have a little ambiguity. We will either run this 2 codes and see what they generate, and then I'll go to the board and do some derivations, which may be most optimal, or I will waste 40 minutes and get you tired with derivation, and then we'll run the codes. But the idea of today's exercise, after we are done with key for the homework, that the
Patrician's waiting at the end of the.
oh, okay. I need to include as much of you as possible into co-hosts so that you can admit each other. Hello, Patricia. Nice seeing you connected. I believe I clicked the button admit. Maybe by an error I clicked reject.
I don't think you can reject. I think you can just exit. So she's just sitting in like the participants thing. So you might have to pull up participants and admit.
Okay. Yeah, let's hope that she will read.
That's his working.
So she's sitting in the waiting room joining.
Okay, so it is a continuous process, present continuous. So let's refocus and complete things in time. So the code that we did use right now compares exact quantum solution, the perturbative solution, and the limit in resonance limit, right? and it gives like 3 lines that coincide at a short time. What if we are interested in a long or relatively long time? Definitely all these perturbative things fail, right? They just go get this quadratic, but the fact how we formulated our approach to solve this two-level system under electromagnetic radiation is not exact, even in a numerical way. So there are numerical regimes when our reference solution that we used as an absolute truth to compare our perturbative solution would fail. And we need to identify this regime when the numerical solution fails, and then explore an easy fix that will counterfight this failure. And the solution exists. These little things, when they are introduced in the textbooks, they are often skipped or not skipped. They are delivered in a so brief way, so that one can just as running in a car on a highway, you may not notice some little details. But this is a critical thing that will enable or disable further progress. So I will make a little stop and focus on important aspect. The name for this trick, rigorously, if one looks into textbooks, most rigorous, it would be converting into interaction picture. But since we will be doing not literally what is introduced as interaction picture in the books, I'll call it a little more humble rotating frame. But it is very close to interaction picture, and it is what will enable our numerical reference solution to work on a long time scale. And if no one objects, I suggest we run all 3 codes, and if there is a time after, I will do some derivations to introduce where this little fix, which is basically just changing a couple of symbols, is coming from. And if some of you have limits in time and need to depart earlier, at least everyone will get acquainted with the codes, and derivations are boring. They can be taken from books or watched in the recordings. So I was not emailing the codes earlier, because I wanted to give chance for unbiased completion of the homework or the report from the last time. I'm going to send the Patricia did submit her thing. Okay.
Pop back up.
But I don't have a button to push.
Press the little arrow.
Huh?
Yes. Okay, so you definitely hit admit that time.
Okay.
She might be having connectivity issues.
Maybe she's not on campus and trying it for somewhere in the city. Oh, Patricia, very happy to see you connected. Hope you can hear us and speak back to us. Okay. So you'll see it in a few seconds. Okay, so please, I believe I did send 3 pieces of code. Please download all of them and run. And let's run together the course disabled sharing screen. It looks like I disabled myself. Okay, let's try. So you should have received 3 scripts, 3 MATLAB codes. So the one with name scan is something that will be a key for the homework. So So I will quickly go over the script itself, but what it does, it focuses on the different values of the offset. So we some of you who did the original way of running this I'm just hearing feedback. Same little box or I hear Adam from. So we were running the code in the resonance, so it is in a unitless when the frequency of flight is equal to the frequency of the transition, like in the 2-level system, and we explore the height, the probability that something have been transferred from ground to excited state. If the offset is selected small enough, then it is a high probability. As far as we increase offset, it drops, right? And there are some fringes. I believe London did like from 1 to 2, something like this on the one side, but on the other, it will go opposite. And we can imagine or even recognize that it looks like sine squared divided by offset squared, right? If you will do it at a longer time, it will get taller and more narrower. And since we proved in the class that the integral under this curve is equals to pi times time, it is a good representation of delta function. If we increase time, it will become narrower. More visitors. Hello, Vova. Nice seeing you connected. So let me quickly go over the script because I read in your eyes that you may not work in this figure. So let's. So this, another figure that I brought to the front, is result of a single run, right? And we are looking onto probability after certain time, like maybe a little bit here, small, about like 5% population. And depending on whether the frequency of the light is smaller or bigger, whether it is in resonance or off resonance, we get different chance, different probability of excitation. So the figure with this resonance condition is the absolute answer for the homework. So expected. Other forms are progress toward the answer. here is the code which you already have. So one does need to enrich our main code, which includes a loop over time steps with an additional outside loop over the energy offset. And here we are setting offset proportional to like discrete number times step size, and then reset value of frequency, value of offset, and then redo the whole dynamics. At the end of the dynamics, we are at the end of the dynamics, we accumulate the population in the state number 2, in the excited state, at the last time step or the same time step, and then this accumulated population at the last step of the trajectory is being plotted against the frequency, which is also accumulated. So these two lines are important. So here we accumulate value of incident right frequency. In the line 78, we accumulate the population, and here we just plot it. So any quick questions about this thing? Make sense? Feel free to ask. Maybe it's not a way to torture young minds. We better have absolutely clear, and we all stay on the same page. So if something looks suspicious, feel free to say. All right. All good?
Yeah, for now, I have questions later.
Uh-huh.
For now, yeah, I have to look at this more.
Okay. Max, does it make sense?
Yes, I'm just messing around with it now.
Okay.
I'm just messing around with my help with glasses, so I can see if I can change the limits, if I can get the other bumps.
Okay. Okay. Yeah. It's fun. Adam, Patricia, Lola, if you have comments, questions, speak now or any other time. Okay, I'm going to wrap up with this homework and invite you to look at 2 other codes that I sent. So
I have a question.
one of them is okay.
So
I will probably hide the microphone. And
can you hear me? So the plot that looks like a Gaussian, is that what the assignment is supposed to look like? Is that what you say it's supposed to look like?
Yes, I understood your question.
Yeah, is it this one?
Yes, confirming.
But I thought you said we only need to change the offset values.
So you can change offset either manually and rerun the code like 10 times. And then you scan over different values of offset, or one can use like reprogram the code and make that the offset is scanned automatically. In some sense, here we have a computational spectroscopy, which corresponds that your diffraction grating is rotated at a small angle, and you heat the sample with the light of different wavelengths.
Okay.
Does that make sense?
Yeah.
Okay. Any other questions? Lola, Patricia, Adam?
Yeah, about Dr. Kalin, this code I was trying to see, it doesn't look similar to what we have on last week. The one that gave the Gaussian shape. Since I was trying to see what changed there in case we want to do it, in case I want to rerun it myself, I was trying to see, apart from the offset, what else, how were you able to modify it? Sorry.
Do you hear me?
Yes, I can hear you clearly.
Okay, I don't know how, but it works. Maybe there is a microphone in the computer. So the central part of the code is the same. So you just propagate dynamics, right?
Okay.
Set up Hamiltonian, set up the evolution operator, and propagate wave function from the past to the future, and then accumulate the wave function in this designated array. But this central part of the code is inside of another loop.
Oh, okay.
Another loop does program the value of the offset to be scanned continuously. So it is two cycles inside each other. And at the end of the code, so I'm looking where the word end happens another time. Screen. So here is end. And close to this end, I do accumulate the population of the state 2 at time step 500 into this array ACC P2, accumulated P2. And then at the end of all cycles, this ACC P2 is plotted, which gives this resonance image. Is it better?
Okay. Yes, it is. Thank you.
Okay, thank you. My pleasure. Adam, if you don't have questions, you can stay silent.
I'm pretty confused overall, but
Really? Why? Please share your confusion. We all want to enjoy it.
Nothing specific.
But are you confused with how the image looks like, or you're confused how to get this image?
I'm working with the code, yeah.
Okay, so but the way how this resonance curve looks like doesn't confuse you.
No, yeah, it's good.
Okay.
Sorry, Dr. Killeen, I have one more question. Last week we were exploring how the population of the ground state and the population of the excited state. Looking at this Gaussian, can we like differentiate?
It's not Gaussian. It is sine squared divided by x squared.
Okay, like Gaussian shape. Okay.
So if you see another little image that I'm showing right now,
okay,
we start at 0 time. Population of ground state is 1. Population of excited state is 0. As time passes by, blue line, population of the ground state decreases. Population of the excited state increases. So
okay.
In this image, we are exploring population of the excited state. When we were meeting last time, we looked on this red curve, solid black, and there is another dashed line, which in this settings, it coincides with black line. So it shows how the population of the excited state changes over time at a short time limit. You see the red line and black line coincide near the origin.
Yeah.
Okay. And the homework that we are discussing right now is, you see the value in here is about 5%, maybe 6%. So it shows what happens at the very early stages, on resonant and off resonant. So not the whole curve, is exploring only small part.
Okay.
Okay.
Yeah, thank you.
Okay, thank you. So let's focus on two new codes. So the one that we added comments last time is almost the same. I just changed 3 lines. And this is intentional. So the So this relays are intentional, and they intend to explore how the system responds to the time step. Instead of setting number of time steps and time increment, here one can set duration of a whole trajectory, and then set up that time increment is duration divided by time steps. So we can use smaller, denser or sparser time steps and explore the same range, so that images will make sense and look similar. In case we do have absolutely correct solution, modifications of these technical parameters like size of grid step should converge and shouldn't change if you modify them. So if I'm going to first I will run, explore what happens, and then if I double number of time steps, nothing should change as a sanity check for the code. So if the amount of time steps and appropriate size of time step are small enough and do not accumulate numerical error, then I'm going to go backwards to reduce the number of time steps. And I was just running it before starting our meeting. So if I go to about half of this or 1/10 of this, so from 1,000 to 100 steps, it creates substantial numerical error, and numerical error that it predicts that there is no excitation from ground to excited. So if you, it doesn't create this crazy numerical error that goes to infinity. It just shows that there will be no transfer. It just stays in the ground state, which you know it is wrong. And then there will be a modification of this code where just a couple of lines are changed, and the same numerical experiment of modifying a number of grid points will not alter the results. So it will be much more resistant to simulation parameters and would allow substantially larger time steps without noticeable decrement in the precision. Make sense? Okay. So here is this experiment. I'm saving, bringing this to the top and running. So I just erase this image so that we, okay. So do you feel comfortable with the image and with interpretation of what is going on?
Yeah. Yeah.
Max?
Why is it?
Okay. So this yellow line, it is shown. It shows on the same time scale and unvariable scale the strength of electric field. So it oscillates very rapidly. and this frequency is set to be equal to once to match the offset of energy levels. So this continuous irradiation of a system will induce full excitation from ground to excited, and then if you keep irradiating, it will stimulate stimulated emission. So it will go back to the ground and then go back up to the excited, and then it will be continuous Rabi oscillations that at one day we can prove in class. So it's one of the simplest problems to prove mathematically. So let's make some. Okay, let's notice. Yeah, and the perturbative solution coincides at short times and starts to diverge, and summation of ground and excited should give one. So you do see that there is a very little oscillations per reflection of this oscillations probably viewed on this population curves, and we have a full cycle in about 650 time units, right? So let's do an experiment, and probably the homework lab report will include just to record what we did and describe. So let's go to the code and double the number of time steps. Maybe if I want to compare, I can even open another figure. And then let me check if I did save this. Yeah, I did. Now let's run. And see that an increment of the time step 2 times, it modified. It made a full cycle instead of 650, it made it like 640. A little quicker. But generally, if you keep increasing, it will stabilize and it will not change. So it is a qualitatively the same picture, and quantitatively there are little changes, right? If you're not sure, let me make one more run. So let's do it 10,000. So we see it maybe went to 630 or 620, but nothing else. And it's a stable solution that is saturates and approaches the regime where it doesn't respond to further change of the parameters. Now let's see what happens if we, let's make it 900. So I have enough patience to run it like 10 times just to see a continuous picture. Save, run, and see what happens. Okay, not much. Yes, please. Reason for what? You can do 800, but if all numbers are factors of each other, there could be pseudo just could they view the pseudo periodic solution. If we do have a sine function with a very fine resolution, and then if you take offset being a if you take grid points about, let's say, 0.9 of the period, then it will pick this number and this number and this number and this number, and it will create oscillations of much larger period, but they will look still harmonic. So it will be a numerical artifact. And I was just playing by having figures not literally factors of each other to see how much it affects. Save and run. Okay, we see it pushes a little further, but still same qualitative picture. Save and run. Pushes further, but we do see this oscillations. We do of electric field. We do see oscillations of population, and by now we still have enough points to represent oscillations of the field. Run. Yeah, let's erase one of them, otherwise it's too confusing. Now the electric field is not as nicely oscillating, it's more like zigzag line, but we are still, the error is like less than 10%. It shows a little slower, but it's acceptable. Keep going further. Save and run. So going further, and we see how the representation of this oscillating field gets less and less informative. Save and run. Now the representation of electric field becomes uglier. It doesn't look like sine or cosine. It's some zigzag, and we have longer time that takes for population conversion from ground to excited and back. Save and run. Now we see some artificial oscillations added to our population curves. The electric field is getting some bits, and it is not actual bits. It's just because of this effect. So we represent fine oscillating curve, but by very sparse grid points. And now the full cycle is already away from our range of exploration. So if you keep going further, run. So now we do see oscillations, but they show much longer period. It's again just representation, picking grid points at some regular offsets. And for the core part of the computer code, it looks like there is something oscillating and it induces transitions, but it is much longer period. So we got another 100 steps less, but now we see dramatic change. It takes substantially longer. 100, save, run. So again, ugly representation of electric field and even longer. If you keep going, it will be something, but approaches of no transition at all, right? And it happens because the I just want all of you to become movie stars. Only Hades and London were in focus. So the reason for this numerical error that the orbital infinitesimal evolution operators, the propagation of wave function, simple two-state wave function forward in time, was depending on instantaneous value of the electric field. And we know that electric field oscillates with time. But if we do not pick the full oscillation, we have number of grid points is smaller than substantially smaller than the period of oscillations, we get something qualitatively wrong. So we may still get some transitions, but they are orders of magnitude smaller, right? And Two of systems are all within our reach capacity of even not powerful computer. But as soon as we get to, and we here explore 1,000 atomic units, which is 42 atomic units is 1 femtosecond, so it's 25 femtosecond. You can do it anyways, all advanced numbers. But if you have something more complicated than the system, if you need more than 20 seconds, this might be an issue, right? We may want to save our numerical effort and having less grid points or same grid points all the time. So one needs to design something, right? And since those oscillations are regular, there should be a way to take them into account without stuffing our time interval with so many grid points. That's some result. Okay. So, and the experiment that we were doing is we were changing number of grid points from 2,000, 1,000, and then from 900 to about 50. And we saw that it dramatically drops the rate of transition and to the level of being correlated. Now let's run the second version of the code that is referred to as PDPT rotated class or rotation in class. So let's set, you see these three lines are identical, and we will go over what is changed in the code. If it will not serve our goal, then there is no reason to explore it. But let's check if it will make any wonders. So save, run, and it shows the oscillations. I was focusing on one board and drawing on another one. So those who are online may not enjoy it. So about 630 is time needed for the full cycle, right? So in our previous life, in our previous attempt, we were reducing number of grid points, and then this return, that the period of time that is needed for system to return into its initial state was moving to the right, to a longer and longer time. This numerical experiment, save, run, and see. So nothing, it's 630. Save, run, nothing, 630. 8, save, run, 630. 7, save, run, 630. Save, run, about 630. Save, run, 630. Save, run, 630. So we see that oscillations are not oscillations anymore, but our solution is not affected. And it is not I didn't put like sine and cosine to represent the solution. It is a numerical solution, is one trick. Let's continue. Save, run, and checks. Since still 630. And there are no this artificial oscillations of population, modulations of populations because of this pseudo base. They're continuous lines as in the solution with a fine dense grid points. 200, save, run. Same place, 630 or maybe 620, but same qualitative way. 100. Save, run. Maybe 620. Right? You see, the solution is very resistant to circumstances. So we have only 200 steps, and it reproduces the same 5, just 50. Save, run, and it still reproduces the solution. So let's make an interview. So what's the secret? Why is this solution gives better?
I wonder if it had anything to do with that effect.
Okay, but can you formulate what should be done? Do not worry to say something wrong. Just make a hypothesis. What should be done to make a numerical solution more stable?
I mean, increasing the time steps is good, but it seems like you can find a certain amount of time steps that matches the frequency, right?
Any ideas? Just put creative imagination. Yeah. There are very tiny changes. You may not notice it if you scroll through the script. Yes. So we need to take into account oscillations in some more regular way than representing them by grid points. We agree?
Yeah.
Okay, good. Can I say any ideas?
I mean, maybe some sort of unconditionals.
Okay, well, there are no boundary conditions for time-dependent problems. There are only initial conditions.
Maybe you can somehow predict the phase on a small scale before it develops over time.
Okay, predict the phase before it develops over time. Really great idea. Here. So since it is oscillatory function, we can predict what it will do. We don't need to be so much dependent on the representing of known periodic function. These grid points. We can just know that it will be oscillatory function instead of taking it numerically. We can take into account information about these oscillations just based on frequency. You notice that for the point of the sense.
Well, okay, so it looks like the original one that we had is essentially, it looks like it's probably taking the previous wave function that we had and then iterating forward one time step based on that previous wave function. I'm not 100% sure, but it looks like this version is, it might still be, the Hamiltonian is definitely made differently, but it looks like it's using the original wave function and basically just extending the Hamiltonian out to whatever time we're currently at.
No, it's see from side to side with details. So it's
Right, yeah, so it's
infinitesimal.
okay.
But you notice,
But it's, yeah, the Hamiltonian is key here.
yes, exactly. Hamiltonian is different. How much is it?
I mean, not that different.
Like what are the line numbers and what is different?
So in the contents code, this is line 25 through 26.
Okay.
And 18 and 19 in the rotation code.
Okay.
I mean, we've got like
Yes. Oh, there I Okay, let's give chance to Lola, Patricia, and Adam to contribute, as you're on the right path. Lola, would you like to share your vision of?
So I don't know, mine doesn't really look like yours, but sorry, what is this yellow line called again?
Yellow line is electric field as function of time represented by grid points.
Okay, so that's the one that I see that kept on changing with the time step.
Mhm.
And then this, the red and the blue, sorry, is what?
They are populations of the ground. Red is population of the excited state, and blue is population of the ground state.
Okay. Mine looks differently populated. Like I don't have it like oscillations like this. I have it as just, I don't know, maybe if I share my screen.
Okay, let me make you a co-host. Stop sharing. Over. Make co-host. Yes. Yeah, please go ahead and share screen.
Okay.
And just to disclose the secret, details will be covered tomorrow by Adam. It's literally his presentation. I don't know if Adam recognizes. Okay, well, which code did you run?
The one that says comments.m.
Okay, and what are your parameters? What is, can you show the code, number of grid points, number of steps, time steps?
I used 201.
Okay, 201. Now, please run the second code, TDPT ROT class with the same parameters and show what happens.
Okay. Okay, it looks like that now. Can you see my screen?
Okay, this is correct solution, and one code fails, another code gives correct result, and we are discussing what is the reason, what has been changed in the code to make it resistant to modification of the grid points.
I really don't know what was changed.
And London did tell which lines were changed.
I guess I can't really hear like.
Okay. I'll try to bring microphone closer to London. London, please tell us which lines in one and another.
So it's the Hamiltonian that you're after. So the TDPT comments code, that is lines 25 and 26. And in the TDP rotation class, that is lines 18 and 19. But the Hamiltonian is made differently. And I'm still trying to figure out exactly where these are coming from. But the one that works better seems to be making, I guess, like more of a direct use of the time evolution operator. Like, I don't know. They're both using the time evolution operator, so it's not like really what's going on, but it's basically just your potential times the time evolution operator and the one that's working better.
Okay, thank you, London. Do you see changes yourself?
Yeah, but the one with comments.m doesn't have an exponential, like it doesn't have the time, the evolution operator, right? It's just
It would be great if you would share the whole display rather than a single
okay.
window, and we can discuss. we are slowing down a little bit, but we have time to complete it. And I think we are getting through this intrigue and understanding it.
Like
Okay.
this has the exponential, which I believe is the time evolution part.
Okay.
But then this doesn't have it. It's just, I don't know. I'm like,
Okay,
Okay.
cosine.
this, yeah, it doesn't have, it's just cosine,
No,
right?
That's the Hamiltonian for the perturbation.
Yes, yes, correct. Okay, yeah, thank you for the good observation.
Is it that we're in the code that's not working as well?
This is the one that is not working. It doesn't have the exponential.
Not working as well. Are we updating the wave functions themselves? And then the one that's working better, we're using the same basis functions, like the same ground state basis functions, but just updating the phase? Is that the difference?
I like your direction of thought. Basically, it is a correct answer. There is a canonical way to express this thought in more standard terminology, but yes. If you would write paper in this terminology, majority of reviewers will not understand what you're speaking because it's too personal and exotic style, but the idea is correct. And there is standard colloquial terminology to express this idea. Yeah, thank you all. Let's ask, so you have identified, Patricia, would you like to share any observations? What is going on and why one code is better than another?
I was trying to hear what Landon was saying, but I could barely hear. But I could see that the code is different from where you pointed out to. But like why it's better than the other, I don't know why.
Okay, but at least you see how they differ. Just in
Yes,
the
I can.
Hamiltonian. Okay.
Yeah.
Okay, thank you.
I can see how the
Okay, Adam, would you like to share screen and share your thoughts?
Yeah, sure.
Okay, thank you.
Do you enable it for me, please?
Okay. You are a co-host.
Okay. Okay. There we go. Well, yeah, so the Hamiltonian sort of made in a different way, but what's different here is that this kind of constructs the matrix differently. Is that an interaction term or?
Yeah, so let's look on the original one with the comments.
Okay.
So what is on the diagonal of the Hamiltonian?
E1, E2.
Energies of eigenstates.
Yeah.
And then Tori was the first who accused me of stealing eigenenergies and replacing them by zeros, right?
Okay.
So both Hamiltonians do have energies of electronic eigenstates, E1, E2, and both Hamiltonians do have a frequency of light, uppercase W.
Yeah.
They are placed in the different ranges. So in the original Hamiltonian, where is the frequency of light?
Sorry, I couldn't hear you. What?
In the original Hamiltonian, where is the frequency of light? Uppercase omega, uppercase W, right here. Just tell where, in which part of the matrix, in which part of the Hamiltonian we observe the frequency of light.
Just in the diagonal, and then in the rock class, it's.
Let's focus on the first one slowly, because so off diagonal, right?
Mm-hmm.
And it is oscillating. It's like cosine.
Yeah. Oh, yeah.
It's just perturbation in respect to unperturbed Hamiltonian. If V is small, then it is just small perturbation. And here the off-diagonal elements do not have energies of electronic states. They have only frequency of light, correct?
Right. Yeah.
Okay, now let's analyze the improved code.
Well, do not have a cosine term.
But imaginary exponential of the same argument will be kind of
Yeah.
thing, right? Including sine and cosine. But this exponential includes not only W, but also something, this E2 minus E1 divided by H bar.
Mhm.
So how will you interpret it?
We have to do with ground and excited state energies anyway.
So H bar equals 1 in these units, right? And what would be the omega subtract energy difference of electronic states?
So E2 and E1 are energy of electronic states.
Omega capital minus difference of E2 and E1. And you can highlight this. Argument of the
Oh, and here.
So and continue highlighting to the end of the line.
Oh, yeah.
Okay. So what do we expect of this expression? What would be the argument of this oscillating complex exponential? What would be omega W capital minus subtraction of electronic levels E1 minus E2? Huh? Offset. And what is our best offset? 0. So exponential to the power 0 will be 1. And the same in the lower of diagonal. Here we have E2 minus E1 minus omega. They just in a different order. First is positive, second negative. Here is first is negative, second positive. So in the best arrangement, if it is resonance condition, powers of these exponentials will be 0, right? So main challenge of the time-dependent phenomena is that Hamiltonian is time-dependent. Time-dependent, that it oscillates. But how much this Hamiltonian is time-dependent? How much? Not much. Right?
We're close to resonance, yeah.
Close to resonance, the Hamiltonian becomes time-independent. And for time-independent Hamiltonian, we do not need small time steps. We can be liberally going on a very big time steps. So by now we do not have justification. How can we transfer the energies of eigenstates from diagonal elements to the power of exponential in the off-diagonal element? But it seems to work, and it seems to make the Hamiltonian time independent. Adam, can you comment on this? Agree, disagree, express concerns or confuses?
It makes sense, yeah.
Oh, okay, thank you for supporting. So the accumulation of phase is equivalent to rotating in the complex plane, right? And we are selecting such system of coordinates for representing Hamiltonian, where off-diagonal element, in addition to this oscillation of with the optical frequency, it also rotates. It accumulates a phase according to the phase accumulation of the electronic system. So we, in some sense, from static system of coordinates in sense of Hamiltonian, we move into in complex plane into the system of coordinates which is rotating. So rotating frame, like complex plane is not something nailed to the board, but something that is rotating as quick as optical field, electromagnetic field oscillates. So it rotates together with electromagnetic radiation. And by changing into this rotating frame, we cancel quick oscillations of the Hamiltonian and come to the time-independent Hamiltonian or almost time-independent Hamiltonian, which is numerically stable. I hear one that is breathing, which means he's thinking.
Did we just make the rotating wave approximation then? Or like, is that not quite what it's?
It's not quite, it's close, but there are several similar things. Rotating wave approximation is also here because we replaced a sign by this exponential. If we would not admit rotating wave approximation, it would have here the second part, the exponential of plus e2 minus e1 plus omega, which would rotate twice as quicker. And then we would not be able to do this fast things. But main thing is that we change Hamiltonian from explicit energies on the main diagonal to energies coming to the off diagonal and help to accumulate phase. And it is something we need to justify. Okay, so the homework is just to summarize pictures and observations that we did. And now I'm going to exhaust myself and you if you do not decide to silently leave by an attempt to explain where it comes from. Adam, if you want, you can stop sharing or you can keep showing it as you wish, but I'm going to focus camera on the board and make some little derivations.
Okay.
Thank you. And as a little heads up, it is very, very close to what is expected from Adam on tomorrow's session. Yes. The reason for 5 minutes long limit is that we all can present in a given time. It was 6 minutes now, I will emphasize it. But there will be additional visitors. You can guess they will ask questions, and having more complete, like thinking ahead what could be questions can simplify it. So it's a balance. Like if I stand up and like give on the title, then visitors may start toasting me. If I show something in more logically consistent, it may reduce number of questions, although not guaranteed. Okay. And I admit I may fail without a cheat sheet. So just in case if we get tired and bored or I fail to to deliver, I'll probably just show the final answer. So in the, I will zoom out. It comes into the transmission. So in the rotating frame, so this is time dependent Schrödinger equation. In the wave function of the system in the rotating frame. And here we should have something that plays the role of Hamiltonian. But instead of Hamiltonian, we do have a subtraction of two Hamiltonians, one Hamiltonian in rotating frame minus Hamiltonian in the Schrödinger frame. This subtraction is responsible for removing energies on the main diagonal, having zeros on the main diagonal. So my main goal is to prove this statement, and I admit that by looking on my notes, I was not able to recognize one of the steps to justify where it comes from. But maybe we can do it together, or I will have an insight as talking and deriving. So suppose we do have regular wave function. Choosing the wave function, C1, C2. If we are going to solve, so we discrete wave function, right? There are no continuous space, it's only expansion coefficients. If we want to propagate it forward in time by evolution operator in absence of external perturbation, we can say that it will be equal to E minus I h bar energy of state 1 delta T 0 energy minus I h bar E2 delta T. Feel free to express your disagreement or concerns or confuses. So I'm just skipping to tell that it is propagating forward by evolution operator that is composed of Schrödinger equation of Hamiltonian. And we can call that wave function which is being propagated forward, we can denote it as the rotated. Have rotation, you have accumulation of phase. So we can convert between rotated and not rotated frames by by the evolution operator. Typically, evolution operator is e to the power where matrix comes to the exponential, but if the Hamiltonian is diagonal, then matrix exponential and regular exponential do coincide. If we do have this linear transformation, linear because it is just linear coefficients applied to those things, what would be, how would one express an transition of operators? So this is a conversion of the wave functions, say Schrödinger, U, say rotated. Can we transform operators? Like if there is a linear transformation for vectors, how do matrices change under the same transformation? What does one do? Based on linear algebra.
I'm just thinking for the interaction iceberg picture, you can multiply by an exponential on both sides.
Yes, both sides. And in linear algebra, if one goes between different linear transformation, if you have operator in the Schrödinger, then by one can rotate it by applying operator for moving forward and backward from left and right, because each operator can be considered as ket and bra, and then this operators one will affect ket, another bra, and then it will convert the whole operator. So vectors are transformed by one matrix of linear transformation. Matrices operators are transformed by two matrices of linear transformations. Agree? No confuses? No one opposes? Okay. So let me practice this little prescription in respect to our Hamiltonian. So I am curious what will be Hamiltonian in rotating frame. And then if I want to do Hermitian conjugated rotation and not Hermitian conjugated, I put here E minus plus I H bar E1 T E plus I H bar E2 T 0 0 E1 E2 0 0 E minus I H bar E1 T E minus I H bar E2 T 0 0. So I just need to practice row by column a couple of times. Row by column. E1 exponential plus I H bar E1 T. Nothing. Row by column. 0. Row by column. 0. Row by column. E plus I H bar E2 T times E2. So we did multiply first two matrices, and then we need to still multiply by R E1 T 0 0 E minus I H bar E2 T. Keep practicing. Row by column will be E H bar E1 T E times E minus I I need to redo it. It will be trivial if you do not have external perturbation. Let's do it once again. I'm going to erase it. Sorry if you were writing up to me. Let's check what would happen if we already have the perturbation. If you have V cosine omega t, V cosine omega t. Otherwise, it will be trivial. They will not change for this transformation. Sorry for the once again. Rho by column. T rho by column. Nothing else. Then rho by column. E plus I h bar 1 t times V sine omega t rho by column. Nothing else. Next one. Row of the first matrix, column in the second one. E plus I h bar to t E assign omega t. Yes. And then last row by last column. E I h bar to t E2. And then to complete the operation, we need to multiply it by the forward propagation of the minus I and t 0 0 e minus I h bar. So the beam transformation matrices forwards and backwards are based on unperturbed Hamiltonian, and the Hamiltonian in the center is perturbed one. So we are looking how the perturbed Hamiltonian is being transformed by going into the rotating plane. So roll the code. E to the power plus I power e1 t e1 e minus I h bar e1 t, and then here we have 0. And next one, row by column. From first element 0, from second element e plus I h bar e1 t, v cosine omega t, e minus I h bar energy 2 t. Row the column. E and h bar second energy time. Value of unvariable perturbation sine omega t e to the power minus 5 over h bar 1 t. And then here we have 0. Once again, row by column. First element gives 0, second will give e plus I h bar e2 t, e2 e minus I h bar e2. So what do we observe? If we perform transformation into this rotating frame, here we have exponentials of the same argument with plus and minus sign, so they will cancel. Here is E2, again this plus and minus sign, they will cancel. So we still have the energies at the plane, at the main diagonal of the matrix. And here we do have the cosine times the subtraction of two exponentials. So if I want to make a shorthand notation, I can just minus E1 bracket T, and then remove this one, right? And here I can do same thing. E2 minus E1 bracket T. Move this one. So we do a sign which reproduces oscillations of electric field and additional factors because of the rotation, because of the accumulation of the phase of the electronic system. And it accumulates as quick as big the phase difference between ground and excited state. Now I'm going to follow suggestion by London. He suggested that we need to use so-called rotating wave approximation, which means we will freeballs the drop terms that oscillate too quick. So I'm going to leave this matrix, which we call H rotated. And I'm going to erase a panel above this and continue there. One E2. Here I can replace cosine by E plus I omega T plus E minus I omega T divided by 2. And then I do have this factor of accumulation of phase. R E minus 1 T. And here I do have B, same representation of cosine, E plus I omega T plus E minus I omega T 2. And here I do have subtraction of the higher energy of one smaller energy, but the sign is plus. E to the power I H bar E2 minus E1 T. So if we open each of these brackets, we will get two terms, E plus I omega T plus I over H bar E2 minus E1 plus second term E minus I omega T plus I over H bar E2 minus E1 T. You're following and you're not objecting yet. Okay. So E2 is bigger than E1. Omega is positive. And we set like this is positive about 1 in atomic units. This is positive about 1 in atomic units. So this factor will oscillate with double frequency. And the two quick oscillations are expected to provide just little modulation of overall population. If you want to be rigorous and we want to go and try to prove it. If you go on the path of poor Weizmann, then it just oscillates too quick to bother about. We do not have enough grid points. So just decline this term and call it rotating wave approximation. And keep this one. So here we have positive +1, here we have -1. So in a resonance, they're going to compensate each other to be almost zero power of exponential. And the same thing can be processed with the top case, but third, since this one is negative -1, we need to keep the first one, which gives us +1. Okay? This one will be dropped. I'm going to erase the lower panel and rewrite what we get. E2 I omega minus E2 minus E1 divided by H bar. E over 2 exponential I minus omega plus E2 minus E1 divided by H bar T. Okay. No I detected until now. This is not yet the Hamiltonian in the second code. These off-diagonal elements look very similar, right? But the diagonal elements are still non-zero. So we need to find a trick that will help us to eliminate the energies on the diagonal. Okay, I'll probably keep it here so that we can return to it later and refocus on another board, and then we'll merge them together. I'm scared to act without a cheat sheet. So from rotated, you can move to Weber by this evolution operator, direct operator of evolution, with negatives in front of energies. If you need to go backwards, it's either -1 or just conjugated, limited conjugated. So the evolution over time, DDT of the Schrödinger frame is independent Schrödinger equation, which is not a surprise for us. Now, I do want to express, here's probably the most important step of derivation. I still have some spot where I'm blanking and can make an error or just skip, but if you do the second person, this one is most important. So we do want to express time-dependent Schrödinger equation in the rotating frame, which means we need to plug in this definition into here. I need time-dependent Schrödinger equation in rotating frame. And in respect to our consideration of perturbations, we assume that we already include the perturbation. So GT is the Schrödinger representation. I put U evolution, which gives us rotation. And this is, I can, if I would be very rigorous, meticulous, and you would have more time, I would put that this evolution operator is in terms of unperturbed Hamiltonian. It took too much notation. So U evolution, rotational, plus minus I bar, present verb. The third mean evolution for a function in rotating frame. So the next step is to consider that both wave function in rotating frame and both evolution operator are time dependent. And if they both are time dependent, we need to practice differentiation product rule. D, U, dt, and psi rotated plus U, T, d psi rotated dt. So there is an equation that I'm still blanking. Maybe we will derive together or just postpone for the future. But current form of this equation is far from ideal because we do not look forward to make our equations more complicated and multiply everything by evolution operator at each side of equation. There are too many evolution operators. And specifically, if we target to develop an equation of motion for wave function in the rotating frame, the evolution operator here is not needed. Right? If we want to derive an equation for this term only, it is our target. We do not need evolution operator. Therefore, I want to cancel this evolution operator by applying an inverse matrix to each term here, u minus 1, whatever it is. Like likely it will be just rotating in the backwards, but just symbolically multiplying. So u minus 1 dt t u right rotated plus u minus 1 u psi rotated dt equals minus I bar u minus 1 h bar Schrödinger u psi rotated. So matrix and its inverted cancel each other. They give you matrix. And here are two equations that probably I need an additional effort to justify. So if we are interested to find evolution of the operator over time, it will be 1 over h bar Hamiltonian and evolution operator itself. This I can justify if evolution goes from 0 to time t, then derivative will apply only to final time, and indeed it will be reproduced in this way. The equation that I really like is that if we multiply this expression by inverted operator, we should get just minus I for h bar Schrödinger filter. I think this expression must be proved.
How did you get the expression in black?
The evolution operator is if one applies derivative, the Hamiltonian will pop up to the front, and then the function itself will be reproduced. But to prove this one probably needs to use the evolution operator in the matrix form that we had, and then maybe I can quickly do it. So if our u is e minus I t1 bar t 0 e minus I h bar t2 t 0 0, and if you do derivative 4 time, it will be minus I h bar n of u1 0 0 2 minus I 2 parts. And then if we multiply it by the operator, the inverse operator, which will be just providing in row by column by rotation in the opposite direction, it will cancel oscillating factors and keep the energies in the value.
In our rotating frame, are we rotating in phase with the electronic wave function or the photon?
Electronic.
Okay. Okay. Then the equation of black makes sense to me.
Okay. So at this point, I did convince myself that from this equation we can get this one. And if it sounds confusing, I'm ready to do it. I'm ready to defend. Okay. Now, if we do believe that you can prove this equation, then we will replace this term here by minus I H bar Schrödinger Hamiltonian. The second term in here, the last term here, it is a definition of transformation from Schrödinger frame to rotating frame. I'm going to quickly rewrite it. So minus I H bar Schrödinger psi in the rotating frame. Yes, I know, but I'm using it to for continuity. Plus ddt psi rotated equals minus I H bar H in the rotated times psi rotated. No, now I can move the camera. So the first term from here can be moved to the right side. And then on the left, you have ddt psi in rotated frame. On the right, you have minus I H bar Hamiltonian in rotated frame minus Hamiltonian in the Schrödinger frame. Psi. So if our rotated Hamiltonian is this one below, and Schrödinger Hamiltonian before without perturbation is just E1, E2, 0, 0. Then by subtracting these two Hamiltonians, we will remove the energies of the eigenstates on the main diagonal. And the only term, non-zero term in the Hamiltonian will be off diagonal elements that include our amplitude of perturbation and exponentials with offsets as their powers. Basically, we are done. So I'm ready to defend and answer the questions, but this subtraction of two Hamiltonians will bring us to the situation that is programmed in the second pose, where the in place of Hamiltonian, we use an object with zeros on the main diagonal, and oscillating exponential I, let's call it just delta for offset, or just offset T E I minus delta offset. So I hope this little derivation was accepted. If it is not, I'm confident to defend it and explain, but you have seen that replacing Hamiltonian by this one, which means we moved into rotating frame, has a positive benefit of being numerically stable and in a good sense not responsive to increment of the time step. How to live with it, how to admit it if we do not have 100% confidence in these boring derivations. The information about energy difference and about frequency of oscillating field is moved into Hamiltonian, and we are literally including the fact that only offset between incident light frequency and energy difference of the molecule matters. And this offset is very close to zero, which means in a certain system of coordinates, we do not need to track fast oscillations and make small time steps. Is it more or less okay? So basically, I think we are done, but let me check. Questions, suggestions, objections, appearance?
All of the above. Okay. So
Let's refocus.
So if this is true,
Mhm.
that means that this term has to be zero. Right?
Why?
Because this equation is this equation without this term. Which would make sense if we're rotating in phase. Right, if you ignore this term right here, this equation is exactly this equation, right? Okay. But if we're rotating in phase with our electronic wave function, that makes sense, right? Because in that frame, then our wave function isn't changing. But then that becomes an issue over here because this should be zero.
Will you repeat why it should be zero?
Because if we're rotating, if our frame is rotating in phase with our wave function, that should make this zero as well. So it means that nothing is happening.
I have a feeling how to resolve this confuse. And we are not supposed to stay here past 7. So if you're already tired and you leave, it's very acceptable. So it is still on recording, and I'll share it. Unless I fail dramatically, and I will be humble to share it. But I hope you will come to the conclusion. So there is a thing that I didn't pronounce explicitly, and it is maybe too late to write back and do right notations, but adequate notations. But there is a fact that one of the it's not only transitions between rotating and non-rotating. One of them is zeros order Hamiltonian without perturbation, and another is Hamiltonian with perturbation. So this one is zeros order, and this one is
First order.
yes,
Okay.
zeros order plus first order, like completely between.
Okay.
And then if they both will be zeros order, yes, it will be zero and the function will not change. And what you're telling would be the Heisenberg representation in terminology that Adam hopefully will teach us tomorrow.
Okay.
So if they both are zeros order, but if there is a Hamiltonian, if there is a perturbation of the first order, then there will be slow dynamics.
Mhm.
How to convert it to the stuff on the other side of the board. So one needs to track back and recognize where we assume the unperturbed Hamiltonian and unperturbed evolution, and where evolution includes the perturbation. The width here should be evolution plus perturbed Hamiltonian, and everywhere else it should be everything else. So this Hamiltonian is perturbed, and all wave functions are perturbed. But the evolution operators here, there, and there are in the zeros order, and they do not include the perturbation. So they are in phase with electronic systems. This you include only accumulation of all phase by electronic system. Well, this Hamiltonian does include interaction with light.
So this is where we're putting.
Right.
This one should be expanded.
Right. 0 plus 1, 0 plus 1.
But these are just the phase. Like you get that.
And those are just phase accumulation. Yes.
Okay.
A little better, or we still need to redo everything with the right notation. To be full confident.
Well, to be fully confident, yeah, I would just have to be careful to go through this on my own. But
Extra credit for finding errors. Yeah, please try to redo.
I'm pretty sure that in one of. I'm pretty sure that I saw this somewhere when I was looking at stuff today anyway, so I think that we probably have a resource for that somewhere.
Okay,
Because I saw this recently somewhere. And I saw it, so I'm guessing that it can be found.
okay. Yeah, thank you for the good eye, and now we do have hypothetical clarification. Right, so to be fully confident, one needs to review everything with right notations from the first step, but if we admit that only one Hamiltonian includes interaction with light and everything else is accumulation of phase, then confuses will go away.
Yeah. Well, because this Hamiltonian is definitely unperturbed.
Right.
So yeah, that's ultimately that has to be what's happening, I guess.
Mhm.
Okay.
Adam, what do you think? Can you bring us more understanding onto the subject through your tomorrow presentation
In 5 minutes.
in 5 minutes?
Perhaps, yeah.
Okay. So the confuse in today's discussion was to carefully annotate the Hamiltonian that only unperturbed Hamiltonian that only accumulates phase for electronic system and perturbed Hamiltonian that includes interaction with light. And it is the main subject of the derivation of the interaction picture. So if you try to bring a focus on this and maybe highlight the notations for unperturbed and perturbed Hamiltonian, it would make all of us happy.
Okay. Yeah.
So, David, thank you for joining. Do you have any confusions, corrections, suggestions, or complaints at this point?
Nope.
Okay, thank you. Lola, Patricia, please share any feedback.
Sorry, I have a question. You mentioned something about an interaction picture. What interaction picture?
Okay. So the wave function and operator in general do serve a practical goal of predicting outcome of observation. Okay, I'll write a little bit on this bottom line. So a wave function and operator are needed just to extract the expectation value of operator. And wave function compared to its initial value, you accumulate phase. Yes, I bar Hamiltonian time H0 and whatever. And here it evolves in the opposite direction, plus I H bar H dot time. So Schrödinger picture, if we assume that time dependence is stored in the wave function, here and there. Heisenberg representation, if we assume that wave function doesn't change over time, but in our expression for expectation value, time dependence is stored in the operator. So each operator in Heisenberg representation is time dependent. But yeah, I was wrong in putting letter 0 here. But if instead of full Hamiltonian, we would put unperturbed Hamiltonian, which doesn't include perturbation, instead of Heisenberg picture, it will become interaction picture. And this is exactly what we did here. So we use different Hamiltonians to take into account perturbation and take into account phase oscillations.
Okay, thank you.
And I hope very much that this will be consistently presented with some either written or copy-pasted equations and terminology by Adam as a big help to the whole class. Yeah, thank you, Patricia, for the questions. Lola, are there any questions from your side?
No, no.
Okay, so the how to say homework lab report is just not equations, only the practical part. Running code a couple of times, making screenshots, and add brief explanations, not just pictures. A paragraph of explanation how to compare the response of the simulation of the codes to larger and larger time step. So it will be a couple of figures and maybe a paragraph of text. And due again by the time of lab next week. Okay, I think we are done. Many thanks for your dedication to the class. I'll be happy to answer more questions, but if there are no questions, feel free to disconnect and depart. Adam, thank you for your thumb up.
Yeah, thank you.
Thank you. David, do we need to discuss anything?
I don't think so.
Okay, then with your permission, I'm going to complete this session.
Yep.
Okay, thank you.